Now in the previous exercise, we looked at a concrete timeline for these two investments in terms of comparing them. Well, let's imagine that we just have $2,000 and we're going to invest it for an unknown number of years. We'll say T years. We want to set up an equation that could be used to calculate the accumulated amount A if we invest at 5.25% compounded annually. Alright, so what do we know here? Well, annually means we're going to have one compounding per year, so that would be n equals 1. We also know the rate at which we're going to invest is 5.25%, so we could say R is 0.0525. I always want it in that decimal form. And we are told that we're investing $2,000 for T years. So that's our principal. P equals 2,000. So there are two unknowns in this case. We're actually talking about T and A being unknown. We want to find an equation that could calculate the accumulated amount. Another way of saying that is we're looking for the model for this situation. Alright, now we know how these pieces of information all relate to each other. We could say A is equal to our principal, we know that's 2,000, times 1 plus our interest rate, we said that was 0.0525, divided by our frequency, n in this case was 1, so that's going to simplify things for us. And our exponent should be n times t, so that's 1t. So a few things will simplify. Inside of the parentheses, we just have 1 plus 0.0525. So we could write this as 2,000 1.0525. And our exponent we could just call t. Now, while we're on the subject of simplifying things, let's complicate something first. This model is telling us what A would be depending on t. So we could call this A of t, right? This is a function where as t varies, A is going to vary also in an exponential fashion. Alright, so that's a good model for the first case. In part B, we have a slightly different situation. We want to find an equation that would represent this situation where our interest rate stays the same, but we compound weekly. So pretty much everything is going to be the same. The only difference is that n is no longer going to be 1. There was 1 compounding per year in the first exercise. In this case, we need to know how many weeks there are in a year. And that happens to be 52. So our setup's going to look a little bit different. We'll have A. Our principal still 2,000. Now we have 1 plus our rate, 0.0525, divided by 52. And our exponent, n times t, remember n, the frequency is 52 times t. Alright, so the interesting thing about compound interest is as the frequency goes up, right, this is going to be compounded 52 times every year, the rate actually goes down. Our interest rate in the first case was 0.0525, and that was an annual rate. Now our periodic rate is very small. It's this quantity 0.525 divided by 52, which if you calculate that, 0.0525 divided by 52 is 0.001. So the effective periodic rate is very, very small, which means that our function will only increase a little tiny bit for every period. Even though there's way more periods where the compounding happens, the function's not going to grow like crazy just because it's compounding more frequently. That rate goes way down by dividing by the frequency, which in this case is 52. Alright, so in the last part of this, we want to compare these two graphs and tables for the two models that we come up with, maybe to see which one's going to be a better deal. So if you go to your calculator and plug both of those in, the first one, 2000 times 1.0525, to the t, we don't have a t, so we use x. And we'll plug in the second function, this time 2001 plus 0.0525 divided by 52 in parentheses, and we raise that to the kind of wacky looking exponent 52x. Now, if I hit graph, and I have a standard window, you know, negative 10 to 10, negative 10 to 10 in both directions, I'm going to see very little. My function isn't going to do very much. Alright, so I probably want to change that window, or my functions aren't going to appear to do very much. So I want to change that window to be a little bit more useful. Well, if I go back to the first exercise, the first part of this exercise, my first function has an initial value of 2000, and it just goes up from there. So if I really want to be able to see these, let me start my vertical axis at, say, 1900, or even 1950. So come down to your y-min, we'll change that to positive 1950. Now your y-max, the maximum, has to be higher than that. So we could change that to, I don't know, 5,000. So between 1950 and 5,000, there's going to be a lot of tick marks. So let's do a tick every, 500. And we also don't care too much about negative time. So I can change my x-min to be -1, so I can see the x-axis. And that's probably enough for now. So if we hit graph, we see the first function, the annually compounding account, filling in. And then the second account will fill in right over the top. It's kind of hard to see. So let's look at the long run. Right now we're only looking 10 years out. So let me adjust my window a little further, and I'll have my x go up to, let's say, 30. That might be too far, but let's see how it looks. Alright, there's my first growth function, and my second growth function will fill in over the top of it. Remember, the second one was the one that compounded much more frequently. Alright, so they're going off the top of my screen now. So let me adjust my y-max up to, let's do 10,000. And I'll change my ticks to be every 1,000 units. Now, it might get kind of slow as you're looking at larger and larger portions of your graph. There's our first function. There is our second function. Now, over time, it was a little bit hard to see this when we were looking at a very small time frame, but over time, that second function, you'll start to notice, is higher. It exceeds your first function. Let me adjust my window back out a little bit further. I'll go out to 40 years, and I'll have ticks every 5 years. I'm going to have to adjust my y-max, because you see we're kind of hitting that upper edge of the window with both of those graphs. So let me go up to, let's say $25,000. Hit graph again. Alright, so our first function growing with that gentle exponential curve, and our second function you can start to see outstripping it. Now, the further out you go, if we adjust this out to 50 years, eventually it's going to be very apparent that the second investment is a slightly better option. The reason for that is that increase in compoundings has sort of a gentle increase effect over time. If you find an account that compounds more frequently at the same interest rate, which is what we're seeing here, that account will ultimately be the better deal. Now, you might have to leave your money in that account for 50, 60, 70 years for that to really pay off, but that is something to take into consideration when looking at investment options. Alright, so let's take a look at the table as well. If we go to the table, my table needs to be cleared out, so you can go to the table settings and tell it that you want it to ask you what values to plug in. Alright, so if I plug in 0, we see that our values are the same, right? The initial value was the same. If we plug in 1, after 1 year, we see t equals 2,105, very exciting for the first account, and t equals 2,107.7 for the second account. So why is that? Well, that's because of that weekly compounding. It has a chance, even though the rate is smaller, to catch up over time. Alright, and let's look out 50 years. Well, after 50 years, we have 25,831 in the first account, and 27,573 in the second account. So, a very slight improvement there. Let's look out 100 years. Well, in the first account we'd have $333,000. In the second we'd have $380,000, so almost $50,000 more if you just leave that money to sit there. So that's kind of a nice exercise, seeing how different changes to the situation affect the overall behavior of the money in an account. You could play around with this where you hold the compoundings the same, say you pick monthly compounding, and see how different interest rates would affect your accounts. So the next